began. I can't begin to know when, but then I know it's going strong. Hands, touching hands, reaching out, touching me, touching you. Sweet Caroline, good times never seem so good. I've been inclined to believe it never would, but now Hello everybody, welcome to this week's edition of Video Notes from Mr. Flugum's General Chemistry class. That's right folks, this is for Gen Chem. And these notes will go on page number 29 in your science notebook. We're going to be talking about this today, formation of multiple ions. Alright folks, so I'm just going to be straightforward with you guys. This is a question that you will find coming up on the test that we will be taking sometime probably next week, okay? And really, I'm going to address this question directly, okay? So the big question is this, right? Tin and lead both form 2+ and 4+ cations. So it's not uncommon to find both, okay? However, carbon and silicon, right, which are in the same group, right? They're in the same column or group on the periodic table. They really generally only form 4+ ions. Why does this happen? How can we explain this? Well, it comes down to electron configurations. Now, just to review this, in case we haven't covered this in class when you do these notes, we have this idea or this theory in chemistry called the rule of octet. Now, it's not a strict rule, and it's also not a law or anything like that, but it gives us a guiding principle for why atoms do what they do. It's called the rule of octet. So atoms are most stable when they have a complete outer level of electrons. So that means their highest energy level, which we call their valence level, is full of electrons. Generally, that means this, 8 electrons. Okay. However, it doesn't always have to be 8. It could be 2. It could be slightly more or less depending on the atom. So let's take a look at these electron configurations. We're going to focus in on tin and silicon, okay, because those are the two elements that are kind of closest to each other, are going to have the closest number of electrons. Now, because they're in the same row on the periodic table, their electron configurations are going to be very similar. You can see here in tin, we have the 5s2 and the 5p2 sublevels, which each have 2 electrons, and in between them we filled up the 4d electron level as well. Now silicon will be similar because it also has an s2 and a p2 valence level. So remember, tin is a larger atom with more electrons, so it's going to have electrons farther away from its nucleus, right, in higher principal electron levels. Alright, so how do these achieve an octet? Well, the easiest thing to do for them is to lose electrons. And that's what metals tend to do, and silicon also tends to do that as well, as it's a metalloid. So, right here, and I've changed the electron configuration around for tin so that we can get our valence electrons together. Tin is going to do this. It's going to lose these 2 electrons here. And what that does is it gives us a full valence level right here, right? As you can see, level 4 is completely full of electrons. That is a stable electron configuration. Silicon is going to do a similar thing. It's going to lose its 3s2 and 3p2 valence electrons, okay, giving it a full second level, right there, which is full, the 2s2 and 2p6. Both of these form 4+ cations because they lost 4 electrons, right? Okay, now when we start talking about the 2+, ions that the larger atoms can form. Here's why. There's some unfulfilled potential. And it comes down to this. If we think about the fourth energy level here, there's a missing sublevel. It's 4F. Okay? And in this case, that has 0 electrons in it. It hasn't been filled yet. Now, what tin and lead can do is they can take this empty F orbital and shove electrons into it, therefore emptying its highest energy level. So what happens when tin forms a 2+ ion is it gets rid of the P electrons and shifts the S electrons down into 4F. This gives it a full outer level of electrons, okay, as you can see right here, and gets rid of these valence electrons that cause instability and have the most energy. Now silicon, on the other hand, cannot do this. It does not have an empty or unfilled sublevel for it to form a 2+ ion. So that's kind of how it works. So to summarize it all, here's what it comes down to for group 14 elements. All right, and we're talking about carbon, silicon, tin, and lead. They all tend to form 4+ cations. All right, and they lose all 4 valence electrons in the S and P sublevels, right, at their highest principal energy level. And that forms a stable electron configuration. However, the larger cations, the larger atoms, can form 2+ cations as well. And that is because they only lose the P sublevel electrons, right? And S electrons get shifted into the F sublevel on the energy level below. So this makes those large atoms able to form commonly two different cations, a 4+ and a 2+, whereas the smaller atoms, the carbon and the silicon, are generally only able to form 4+ cations. Well, thanks for tuning in, folks. I hope this made a little bit of sense for you. And like I said, this is on the test, so focus in on it, see if you can put some thoughts together, and ask questions if you need. We'll talk about this on class on Thursday or Friday. Thanks for tuning in. Hope you have a great day. Bye-bye.